Hello again, everyone. Welcome to week 3 lecture. This week we'll cover the very end of chapter 2 and begin chapter 4. Okay. So we kind of skipped over section 2.8. We won't do much from there. So no, section 2.8. Section 2.7 and 2.8 contain some ideas that will I'll remind you again if we need them in the future. Anyways, so let us quickly cover the tail end of chapter 2. This is not a major chapter. The big chapter, it's a really concern yourself with, is chapter 2.6 or section 2.6. A lot of content there from the last lecture. Anyways, to finish up this chapter, we'll look at the following collection of equations. And so we won't treat these like, they're called autonomous equations. We won't treat them exactly like the other classes where we try to find explicit formulas for solutions. These are all separable, so they fall under that category. But we'll just be able to analyze the solutions to these equations without having to solve them using kind of the ideas of the slope fields. Okay, so we look at this class of equations where the right-hand side does not involve any variable. So here we're looking for an unknown function y of variable time t, and the differential equation that we want y to satisfy doesn't involve t whatsoever, just y itself. Okay, for these equations, they arise here and there, but the main thing to keep in mind is, or you can always think of them as describing the height of a particle. You know, you imagine you just have a line, you fix some height 0 to be 0 ground level, and then what y is describing over time is kind of the height of the particle over time. Here I'm drawing, you know, a little, well, you know, if I drew what I just did as time varies, it was, you know, it looks like, you know, some particle going up and down. Okay, think of y of t as the height of a particle. What will be important to analyze these functions is what is the right-hand side of the equation graphed over what's called the phase line, which is just the y-axis. Okay, so we're going to be analyzing not the solution, not the graph of a solution, but the graph of the right-hand side of the differential equation itself. So what I'm trying is this is not a solution curve, and it's a different type of object. It is the graph of the equation over the you know, the right-hand side of the equation over the phase line. Okay, so what's going to be very important, we saw this before with some examples in the slope field section, but we'll see it in more detail here. The zeros of the right-hand side will be very important for equations like this. They'll be called equilibrium points. And then if you have a point, say y0, where the right-hand side of the equation happens to vanish, is, you know, it's 0. Then you call it the constant function y of t equal to y0, you know, just the constant function that's always equal to that value. That'll be a solution to the equation because the derivative of a constant function is 0. This is a solution to the autonomous system because, okay, on one hand, the derivative of this function on the left-hand side of the differential equation, that's 0. So this would be 0 for this constant function. And on the other hand, when you plug it into f, you get 0 because that's where we got it from in the first place. So this is also 0. So these constant functions solve the differential equation. So you call them, that justifies the name equilibrium solution as well. Okay, so let's take a look at a little example here. We're going to want to describe the behavior of solutions again, just like in when you analyze a slope field, you don't need to necessarily solve the equation to analyze all of its long-term behavior. Let's see what we mean here. So let's use slope fields to kind of answer this question. Okay, so so let's draw two pictures here. Let's draw a slope field. And on the other hand, let's think of this as that f of y, right-hand side of the autonomous system, and graph that. So let's graph that over here, over the phase line y. Okay, so let's take a look at this right-hand side here. This is equal to 0 when, well, either y is 0 or y equals 5. No big deal there. So, y is 5 and 0. We got some special points there. That's where the function is 0. And then let's see what's gonna, let's try and sketch the rest of the graph. Well, it's not hard to see that if you are to the left of 0, then this expression here will be negative. And then it'll be positive, and then it'll be negative after the second 0, 5. Okay, so this is a sketch of the graph of f. Okay, what does that mean for the slope field? Well, maybe I shouldn't use. Let's go here. Okay, the slope field, there's going to be two important heights. Okay, so let me take a step back. First of all, because this is autonomous system, there's no variable on the right-hand side. The slope field will only depend on height. It'll be totally the same as you go left and right. The little slopes of lines will not change as you go left and right, only up and down. And so, for instance, at height 0 and 5, the right-hand side is 0, so I should be drawing horizontal lines there, slope 0 lines at height 0, and then at height 5, I should also be drawing horizontal lines. Remember, to make a slope field for a differential equation like this, at every point x comma y, or well, yeah, t comma y, either way, you should draw a little tiny line segment, the slope of which is the value of the right-hand side of the equation at that point x, y, or ty. Since the right-hand side vanishes for these values of y, we get 0 slope lines. Anyways, so let's take a look at this picture up here, the graph of f, and use that to help us complete the picture downstairs. So in between 0 and 5, in between height 0 and 5, f is positive. So f is positive in between 0 and 5. That means the slope of these little lines I draw here should be positive. Let's not get too detailed. Let's just draw some positively sloped line segments there. Again, doesn't depend left or right, only up and down, because the right-hand side only depends on y. All right, and then as we go above height 5, f becomes negative. So I'll draw some downward slope lines above height 5. And what about below 0? Well, f is negative there, so that means I should draw negative slope lines down there. Okay, so now we've done, I don't know, you could call that phase line analysis or slope field analysis of this differential equation. Now let us use that to describe the long-term behavior of solutions. Well, notice, suppose you take some initial conditions and, purple, I don't never use that. Take some initial conditions and draw some solution curves. The fact that above height 5, the slopes are negative, and a little bit below height 5, the slopes are positive, that forces solutions to tend towards 5. And then the different story happens when you're below 0. When you're below 0, the slopes are negative, so that forces solutions to decrease. So what will happen is, I wanted to describe long-term, or I wanted to describe behavior of solutions, I can answer in the following way. And really, this question is a little bit too vague. Of course, if I were to ask you this, I would be more specific, I would say, by the way, I want you to compute the limit as t goes to infinity of a solution. But we'll get to some examples that describe that in more detail. Okay, so I would just say the following. So my answer to this question or request would be to say, so if y of 0, the initial condition, is bigger than 0, so if I start out up here somewhere, above height 0, doesn't matter if I'm above 5 or below 5, as long as I'm above 0, I'm going to tend to 5. The limit as t goes to infinity of y of t will be 5. Whereas if y of 0 is negative, the limit will be minus infinity as t goes to infinity. That's like in the bottom line there. And then if y of 0 is actually equal to 0, then you're just always 0. Then y of t is always 0. Okay, so I've described entirely, I described what happens when the initial condition is bigger than 0, when it's less than 0, or when it's equal to 0. You get these answers. So that's described behavior of solution. Okay, so let's develop a little bit more terminology here. This will be, this is a little bit of a one-off section, but these ideas will come back later in more complicated forms in later sections. So, that's why we're introducing them here. So it's you see them in a little more down-to-earth scenario. Anyways, let's take a look. So we're looking at a autonomous equation, just like we've been talking about so far. And suppose we have a equilibrium point, a place where f vanishes. This is called stable if you have that behavior like before. That behavior of 5 there. 5 is a special equilibrium solution, which is attracting things. And we would call that stable. So such an equilibrium point that attracts nearby solutions to it is called asymptotically stable. Another way of describing this is this is the situation where if you graph f in the phase space, and then here it'd be y naught. So the way of articulating the attraction is by saying f is positive before y naught and it's negative afterwards. So exactly like this situation. So f is positive before and then f is negative after that equilibrium point. So that means that that point will be stable, the definition, and then otherwise you would call it unstable. Okay, so let's do this procedure again for a slightly different differential equation, and let's sketch the graph and figure out what are the stable points. Okay, so let's see. This is f here, so f of y. Let's write it in a. We want to figure out where the zeros of this function are, so let's write it as about y. I'll factor out a y, and then I'll be left with 9 minus y squared. So f is 0 when either y is 0 or y is plus or minus 3. Okay, so let's take a look. We want to get an idea of what the graph looks like. By get an idea, I mean put the zeros on it, put the equilibrium points on it, and then figure out what the sign of the function is in between the zeros of it. So you got minus 3 over here, that's the first one. You got 0 here, and you got 3. We want to figure out what's the sign of this function in those places, in between. Okay, so just imagine what if y is very negative. well, it's not so hard that it will turn out to look like this. It'll cross through like here. And now what happens when we plug in a value of y that's a little bit bigger than 0? Well, that'll be positive. And then what happens when we plug in a number bigger than 3? It'll go back to being negative again. So that is a brief analysis of the equilibrium points. Okay, so let's figure out what's going on. So let's draw a little bit more on this picture to remind ourselves what the sign of f means for the solutions, whether the equilibria are stable or unstable. So let's draw a little bit of arrows on the picture to just remind ourselves of what the derivative being positive means. Okay, so the derivative of the solution, which is y, and the derivative of that thing is f of y. Anyway, so let's take a look at this equilibrium here at -3. F is positive before it, so that means that solutions want to increase into that -3. Afterwards, the f is negative, so that means that solutions that are above, that have values above -3, want to decrease. So they want to go towards that -3. Likewise, if you're a little bit below 0, you want to get away from 0 because f is negative. That means your derivative of your solution is negative. So the solution tends away from 0 if you're below. If you're a little bit above, you also tend away from 0. You want to get bigger because f is positive there. So you draw a little arrow pointing in the direction that the solution curve wants to go in when your solution curve has values near that point. Likewise, over at 3, it looks like the function wants to increase into that. And if your solution is a little bit bigger than 3, this wants to push you down. Okay, so the equation wants to push you down. So we got 2 stable points. So plus and -3 are stable, and 0 is unstable. Okay. Now I would like to, can I move it? I can move it. Very good. Okay, so the next, yeah, so let's keep that there. Very good. So now let's do, the point of these problems is to, the point of differential equations in general is to predict the future. Based on a law, physical law, that a quantity needs to satisfy, you want to use the equation to predict what's going to happen in the future. You want to predict long-term behavior. So let's do that. That's the point of analyzing these points like we just did. So now let's figure out what's the long-term behavior of solutions. Okay. So I don't have too much space. I'll zoom in a little bit. I can't zoom in too much. Okay, so so first of all, let's go from left to right. So what happens if our initial condition is to the left of 0? Well, anywhere to the left of 0, it looks like -3 is going to attract it. So if y of 0 is less than 0, then the limit of y of t as t goes to infinity. I won't write that every time. Well, why not? What the heck? Then this will be 3. On the other hand, if you start out positive, then that 3 is going to be wanting to, that 3 is going to be gobbling you up. That's going to be attracting solutions. If you're bigger than 3, as we see, the f will be negative, and that forces you in the 3 direction. If your solution is in between 0 and 3, your f is positive. Hope I didn't say positive before I meant negative. If f is, then if you're between 0 and 3, then f is positive, so that pushes you up into 3. Right. So from that discussion, if y of 0 is positive, then the limit of the corresponding solution will be 3. And of course, last time I meant -3, because the -3 is the attractor there. And then there's the third possibility. What happens if f is 0? Well, that's another equilibrium point, so it will just stay, if that's a solution, so it'll just stay 0. So if y of 0 is 0 itself, then you just always stay 0. So y of t will just be always 0. So that's like the, let's do that. That would be the analysis, the long-term analysis of solutions to this differential equation. Okay, good. That's all. That's the main point there for that section. So the main point is, if you have autonomous equation, differential equation, where the right-hand side does not involve the all these bugs, where the right-hand side does not involve the variable, then everything is determined by just the analysis of the function on the right-hand side. All the long-term behavior just comes down to looking at where that function is positive, negative, and 0. Okay, that's the upshot. And the only thing you would be asked to do from that section. Okay, so let us move on. All right, chapter 3 involves some particular applications, which we'll skip for now. We might return to it, but we skip it for now. So let's move on to kind of one of the, a section we'll spend a fair amount of time on. So you consider chapter 1, or sorry, the first chapter we looked at, chapter 2, kind of a warm-up. We studied some first order equations, got some perspectives on them, solved certain particular classes of them, the linear ones, the separable ones, the homogeneous ones, the exact ones, and some other ones where you can turn them into exact. But I consider that kind of a warm-up, important things to know, and we'll continue using those skills that we learned back there. They'll always be relevant. But now considering differential equations that involve 2 derivatives and 1 derivative, and the function itself and the variable. So something that looks like this, where the right-hand side is some amalgamation of the function, derivative, and the variable. So as I was kind of alluding to, this is second order equations are very much the way we articulate physical laws. For instance, just to get a rough idea of why this is like a fundamental, area that we're entering here, Newton's second law about, motion of objects says that, force is equal to mass times acceleration. So if you act on something with a force, then the resulting acceleration you can compute with this formula. And if you think of x as the unknown function, so you have the x-axis here, 0, and you got some particle moving to left and right that you're acting on, perhaps, then it says that the force that you're acting on the particle with is equal to second derivative of x times the mass of the particle, which is a second order equation. So right off the bat, a very fundamental example here that we're going to be describing or spending a lot of time with. It's a second order equation. And so this is a physical law, Newton's second law, that is naturally interpreted as a second order differential equation. And this is very, not just the moving of a little particle around here. It's much more fundamental than that. This is a much wider world, second order differential equations. We're going to be focusing in for now on linear equations, things that take this form, where the y primes, the y, and the variable are not so jumbled up with each other. The y prime appears in a very simple form, just being multiplied by t stuff. And the y itself appears in a very simple form, just being multiplied by some t stuff. And then maybe there's a right-hand side, g. There's only t stuff. Okay. This is a generalization of that, linear first order equations. It looks at a very similar form, except now we just have another derivative. Okay. So again, and also from that section, we have a similar vocabulary. If g is 0, if the right-hand side of the equation is 0, we call the equation homogeneous. Otherwise, you call it non-homogeneous. And this won't be, I'll remind you of this when this is necessary. It won't be for this lecture, but in the next week it will be, I think. So sometimes if you have a non-homogeneous equation where that g is not 0, it'll be, not just sometimes, it will always be useful to consider the associated homogeneous equation. So if you have something like star up here, where you have something on the right-hand side, it will always be important to analyze the homogeneous equation associated to it. I only say that, just to introduce this vocabulary now. We won't use this idea quite yet. First, we're going to be focusing in on the homogeneous situation, where we just study the homogeneous one. We don't try to solve some non-homogeneous one. Okay, but just to give you an idea of the main fundamental physical interpretation of these equations, which we'll return to again and again, and we'll study in depth. Let's look at like a mass spring system. So let's imagine the following situation. You have up on your ceiling, you screw in a spring. You think of a very powerful spring, and then attach a weight to it. And then, it's being acted on by several things. You got gravity going down, you got gravity acts on it. And then you could imagine you pull it down a little bit and let it go, and it goes, you imagine it making a little spring oscillating up and down behavior. So, if you pulled it down, then the spring is acting in an upwards way. Spring's acting on it upwards. And then you could imagine there's also like a dampening force acting on it. Damping force acting on it, from like resistance of air. If you go too fast, then that will impede, that'll act, that'll act like a force slowing you down. And then there could be some external force acting on the whole shebang. Like maybe this is all taking place in a box, like on a train, and the train is moving up and down, and that's acting on you as well. Okay, so suppose you have this situation, and you so suppose if you leave the spring alone, it'll settle down to a certain height. Let's call that height 0. And then from that point, let's measure, if the spring is moving, let's measure the distance between the center of the weight and that equilibrium rest place. So that's what I say here. So let x of t be the distance between the weight itself and the equilibrium position of the system. By equilibrium position of the system, I mean just the location that the weight tends to if you just leave it alone for a while. Okay, so just like I said last time, Newton's law relates forces acting on the weight to the second derivative of x. Second derivative of x is acceleration. Newton's law relates that to the forces. So you get an equation like this. Okay, so let me just draw a picture to explain what these things are. So this is this on the right hand side, this is total force. I'll explain each of these terms individually. Not that big a deal, but I will. And then the right hand side or the left hand side is mass times acceleration. So this whole equation is just Newton's second law. But then let's calculate, or let me describe what the right-hand side is in terms of total force. So this first term, so here the K, M will be constants. This first term, well, that will come from the spring. That's how spring is acting on the mass. So this is kind of the nature of the spring. The further you get away from, so here's this mass here. So if this is x of t, as just by definition. And how does the spring act? Well, the further you pull it away from the equilibrium point, it will act in the direction of the equilibrium point in a magnitude proportional to how far away you pull it. That is the nature of the spring, how it acts. So that is exactly this term here. This is like there is some number k, so that this force is equal to minus k times x. So it'll act downwards. If x is positive, that means you're above the equilibrium point. So then the mass will be pushing you away. And if x is negative, you're below, like in the picture here, then the force is acting upwards. K is some positive number. Anyway, so this is the form that the action of the spring takes on the mass. You got gravity over here, just mass times acceleration. Gravity is acting on you. If you interpret g as negative 10 or what a negative number. G is the acceleration due to gravity. And then B here, this is the damping force. It could take various forms. But the thing to keep in mind here is that it depends on the velocity of the spring. Air resistance will dampen your motion more when you're going faster and less when you're, the dampening effect depends on how fast you're going. So that dampening term will usually come in the form a number of times x prime. And then every other, miscellaneous external force, I'll just write as capital F. Okay, so I just, and this one is due to gravity. Anyways, I just present this big formula here because this is the most general form that an equation of motion that we'll consider here will take. We're not going to start trying to solve this equation right off the bat. It's kind of complicated looking, but we'll get there. Okay, so let's consider a basic example. This should be X. Let's consider a basic example where there's no damping. Physically, let's imagine you got a mass and it's on some greased table here, so there's no friction and there's no gravity because it's horizontal. And then as you let go of the spring, you stretch it, you let go, then the motion will be going left and right, be oscillating left and right. Okay, and then if you take so no external force, no damping, no gravity, and then if you write down that equation that we just looked at here, everything except the spring disappears, and you're just left with this simple looking system or differential equation. So, you can imagine, so, the prototype equation would be if, that number K, that depends on the spring, M depends on the weight, it's the mass. So, those are just numbers, but the prototype is something like x double prime is equal to minus x. That's the most basic equation of this form. And it's not so hard. So let's read out in words what this equation is saying. That's saying I'm looking for a function x of t, so that if I take two derivatives of it, that is equal to minus the function itself. Okay, so you could think for a second, do I know a function so that when I take two derivatives of it, I get back minus itself? And you do know functions like that. They're sine and cosine functions. So these will be solutions. So this is, this is like introductory section to this chapter. So I'm giving you an idea of what to expect here. So for this equation, we get sine and cosines solving our equation. In particular, if you want, so again, this should be x here. I forgot to type that in. But if you want the constant to work out correctly, so that when you take two derivatives, get the chain rule twice, you get two copies of the inside multiplying each other. You want that to be k over m. You got to put the square root there. So that's where these constants come from. But the point is that it's a cosine function times cosine function and sine function to solve this equation. And let me say the most general solution to this equation will be the following form. It'll be some combination, a linear combination of those sine cosine functions. So in this formula here, C1 and C2 are any numbers. It's a fact that this formula here is the general solution to that above star equation, that simple second order linear equation, homogeneous, because there's no t term floating by itself. There's no t at all. Okay, and let me just say that there's a general phenomenon that we see here. So first of all, we're getting sines and cosines. Second of all, we're getting two kind of quite different looking functions that solve the equation. Yeah, so these equations that we're looking at, they're second order. So they involve taking two derivatives. You would imagine that if you have to solve for the solution, that's like it's trapped behind two derivatives. So you would have to kind of integrate twice in order to obtain the solution. So when you integrate twice, you get two constants of integrations, and that's a general phenomenon. I mean, that happens all the time. So a solution, you have to specify two constants in order to determine the solution uniquely. So this C1 and C2, they're independent numbers. You make any choice for either of them, you get a solution. So you have to, specify two constants in order to specify the solution uniquely. And so to specify a solution uniquely, you have to specify two initial conditions. So here's a typical initial value problem. You would have some second order equation. I don't know, x prime prime is equal to, minus x. You would specify some initial value of the function, say at time 0, I want this to be 5. And then you need to specify another piece of information. That could come in the form of, say, another value of the function. Or you could even specify what you want the derivative of your solution to be at a given time. Say I want the derivative of my solution at time 0 to be 0. These two pieces of initial data will uniquely determine the solution. Okay, so initial value problems for second order equations or higher order, they take a different form. You'll have to specify two pieces of information. You could specify, maybe for some equations, it could be like you want to specify two values of the solution at two different points. But often you'll want to specify a value for the solution at some given point and a value for its derivative at a given point, like I just wrote here. Okay. Before we jump into solving these equations and describing any method for them, it'll be real confusing if I don't say some basic things first. So let me describe some basic structure of these equations, structures of solutions to them. So we're going to be approaching these equations in even more simple form of these equations, but just homogeneous linear. So right-hand side is 0 and it's linear. So let me just say you some facts. Here's one fact. If you have any two solutions to this equation, then any linear combination of them will also be a solution. And by linear combination, I mean you just take your two functions, you multiply them by numbers, different ones, and then add those things together. That gives you a new function y, and the nomenclature is linear combination, like in linear algebra. Okay, so that's a very special property of linear equations. It was the same back in chapter 2 for those equations as well. But here it's more relevant because you need two constants. It wasn't really relevant in that one in the last section, last chapter, because you were only going to have one constant. Anyways, it wasn't so interesting back then, but now it will be very relevant. The fact that linear combination of any two solutions is another solution. Okay, so we know we can do this, and we know that generally speaking, we need to specify two numbers in order to specify a solution uniquely. So I got two numbers here, right? I can play around with those two numbers. And so the question is, are those the two numbers that will specify the solution uniquely? This is the same as asking this question. When are two solutions, say y1, y2, different enough so that the general solution is just obtained from linear combinations of those two solutions? So notice, so just to look at the above example. So we had two solutions. Y1 was like sine of x or sine of t, and y2 was like cosine of t. These two functions are different enough to give you the general solution, which is just, so the general solution is just, c1 times sine of t plus c2 times cosine of t. That's what the general solution is. So we obtained the general solution from linear combinations of two given solutions. However, so note, so linear combinations, so linear combos, would not give the general solution if, say, we had chosen, okay, so I know I got one solution, it's sine of t. I got another solution, y2, it's like a 5 times sine of t. That's another solution. It's different than y1. So I got two solutions. Let's take linear combinations of these two solutions. Maybe that'll give me the general solution. Well, it won't work because they're like basically the same function. You will never be able to get that cosine solution just from combining sine and 5 sine. So this is like a, even though these two functions, they do solve the equation, but they're somehow not good enough to give you the full set of solutions, the most general solution. So that's what I mean by this question. When do we know when we have a good collection of two functions that will give us the general solution through linear combinations? Okay, and this is the notion. We need the functions to be not linearly dependent. So linear dependence is bad, and two functions are said to be linearly dependent if you can write one as a multiple of the other one. So that c is a constant. That's what it means for two functions to be linearly dependent, just like, that's what it means for two vectors to be linearly independent. The analogy being, we're thinking of the functions as vectors. And how do you tell whether two functions are linearly dependent or not? That's going to be the relevant question, right? Because we want to know when we have two functions that will give us the full set of solutions. That will be exactly when those two functions are not linearly dependent. So we want a way of detecting when are two functions linearly dependent. Okay, sometimes it's going to be obvious, like if you have the function sine and the function 5 times sine, those are obviously linearly dependent, but it will be important going forward to make sure we have a way of checking when two functions are just multiples of one another. Okay, so here is the fact and definition. So two functions are linearly dependent. That's the bad one, where one is just a multiple of the other one. So that one is multiple of the other one exactly when this quantity, the Wronskian of the two functions, which is determinant of this matrix, where you have y1 and y2 as the top row, and then their derivatives as the bottom row. If the determinant of this thing, which by the way is y1 times y2 prime minus y2 times y1 prime, it's just determinant product of diagonal minus product of the off diagonal. If this quantity here, which is a function of t, vanishes. It's a little bit of a mouthful, but if you calculate this Wronskian, determinant of this matrix, aka this quantity, if that vanishes for all t, if it's a zero function, then your functions were linearly dependent. So if that quantity is not zero, then they are not linearly dependent, and so that's the good situation. If you compute Wronskian, you get not zero, you're good to go. You have two functions which are not multiples of one another, and linear combinations of them will give you the general solution, which is basically what I'm saying right here. So if you have two functions that are solutions to your equation, and they are not dependent on one another, they're linearly independent, aka Wronskian does not vanish, then the general solution is just given by linear combinations of the two. So that narrows down our whole focus here. If we want to solve the second order equation, second order linear homogeneous equations, these equations, the goal is going to be find two linearly independent solutions. Once we do that, then we can just write down the general solution as a linear combination. So that I need to tell you this kind of these theory facts in order to get a strategy down in order to try to solve the equations. We need to find two solutions that are linearly independent, then linear combinations will do the trick. Okay, so that's the structure part. Now let's enact it a little. I mean, yeah, we're here. So let's make sure we understand what was just said. I said a lot of math facts, and let's make sure we know how to wield them, kind of, or what the relevance is to the differential equations. So let's consider this situation. So let's look at this differential equation. Second order, it has, it's simple looking. There's no t's present, and you can trust me, maybe, but I think it is a fact that these. I mean, it is a fact that these two functions, e to the minus t and e to the 2t, will solve the equation. So I'm doing the hard work for you. I give you the solutions right off the bat. Here are two solutions. Okay, so let's try to find the specific solution that satisfies the initial conditions y of 0 is 0 and y prime of 0 is 1. So I found I basically found the general solution. So the general solution to this equation is c1 times e to the minus t plus c2 e to the 2t. Since, by the way, these two functions are linearly independent, you don't need to calculate the Wronskian to tell that they're not just a multiple of the other one. Again, when you just have two functions, it's not, you got to be pretty tricky in order to write down formulas for two functions that don't immediately look like they're multiples of one another, yet actually are. Anyways, there's no trickery here. These are linearly independent. So the general solution looks like this, just linear combination of them. So we already have that. Now we want to figure out what are the values of the constants that make this general solution satisfy these two initial conditions. Okay, so let's do that. So note, I want that at time 0, I want to get 0 out of this. Well, what does that mean? Let's plug in 0 into the formula for the general solution. I get C1 plus C2. I want that to be 0, okay? Or in other words, C1 is equal to negative C2. Okay. Now let's write down the second one. Second initial condition, I want the derivative to be equal to 1 at time 0. So let's compute the derivative. The derivative is minus C1 e to the minus t, and then plus 2 C2 e to the 2t, just the chain rule. So the condition that y prime at 0 is equal to 1, let's see what that means in terms of C1 and C2. Let's plug in 0 there. So y prime at 0 is minus C1 plus 2C2. And that should be 0. Okay. So I got two equations here. They're different equations. And I want both of them to be, two equations, two unknowns. We're in business. We should be able to figure out what these two functions are, or these two constants are. So let's do that down here, maybe. Okay, so I know that C1 is equal to minus C2. So this second equation tells us that C2 plus 2C2 is 0. Well, that only happens if C2 is 0. Oh, sorry. I'm gonna undo that. My mistake. I forgot this should be a 1, not a 0. Yeah, if you specified, never mind. If you specify initial condition 0 and y prime is 0 at 0, then the show's over. You're not going to get anything interesting. Anyway, so let me write down the correct thing, which is that C2 plus 2C2 is equal to 1. And so C2 will just be a third. And then, so C1 will be minus a third. And together, the specific solution to this initial value problem will be minus a third e to the minus t plus a third e to the 2t. All right. So we did, the general solution was given to us, but we just got a little practice finding the specific solution, given some initial conditions. Okay, so section 4.2, there's not much in it, but let me just say some words at you to, this might be relevant going forward. It isn't going to be immediately relevant, but it's very short. Let me just tell you that, okay, so just to approach, kind of a heuristic approach to the second order equations. Remember early on in chapter 2, we got a good way to visualize what solutions might look like by slope fields. We said, okay, sometimes you can just get a good idea of what's going on with an equation by drawing the slope field. And yeah, you can predict the long-term behavior without even finding, without even solving the equation through a slope field. We won't do this. So, I mean, for second order equations, the story is much more complicated. You don't have just a formula for the derivative of your function. A second order equation is much more complicated. It's saying a lot more about your function. All right, so let's go through the things that you can do in order to visualize your solution. So on one hand, you could just try to draw the graph, try to find a solution and then graph it. That gives you an idea of what the solution looks like, of course. Another thing you can do is plot the derivative. You could plot the graph of the derivative of the function. And then another thing you could do is over the phase line, remember that, nomenclature, you could plot the derivative. So here you could plot the curve y of t comma v of t, and this is this yv plane. And then this curve will be some kind of maybe spirally thing. That's y of t, v of t. That point there. That could give you a good idea of what is going on with the solution. It's called the phase plane. This y v plane. But again, I'll mention. I just want to say those words at you, and then later on we'll actually, work with the idea more seriously. But for now, it's just the idea. These are ways. I just want to tell you that it can be hard to get a holistic understanding of a second-order differential equation because it's encoding a lot more subtle information than just a first-order equation. It doesn't just tell you what the derivative is; it says something a little bit deeper about the function. And to do that, you're going to need some more, elbow grease. And one of the things that will be useful is to consider this idea where you graph the curve, which is the value of the function and its derivative. But anyways, that's all I want to say from this section. And what we really want to get into is, I have up here, start solving some of these equations. So far, we haven't really solved any yet. And the first one, the first type of second order equation is going to be the most simple one, which is this version of the equation where P and Q was homogeneous, so the right-hand side 0, and P and Q are just numbers. So this is constant coefficient, linear, homogeneous. Second order equation. You wanted to say all the, qualifiers. Okay, so let's, this is one of the most, one of the most simple forms that these equations take. Let's try and start there, figure out how to solve it. So here's a very simple example of one. Let's try and think of a function so that when you take two derivatives of it, you get the function back itself. Here's a very simple, different second order equation like this. Here P is 0 and Q is -1. Well, I know a function that has the property where you take two derivatives of it and you get itself back, e to the t. That's a solution to this equation. And we saw before we had a lot of exponential solutions to these equations. The e to the -t and e to the 2t. Those were solutions in that other problem. And also from first order equations, we had that integrating factor that was e to the antiderivative of the number next to the unknown function in the first order equation. If that thing was constant, then you would just be like e to the t. So this leads us to the following kind of guess. So we're going to guess a solution to this general constant coefficient equation in exponential form. So we have a lot of evidence that, well, it seems like a lot of these solutions are going to be exponential functions. So, we encounter some sines and cosines as well. Let's ignore that for now. We encounter a lot of exponential functions. Let's guess that we have a solution to this constant coefficient equation, which takes exponential form. It's just e to the lambda t, where lambda is some number. Okay, here's a fact that's not hard to see. If you want to test out what number lambda makes e to the lambda t solve that equation, well, that's the exact same thing as saying that lambda solves this quadratic equation, which is, by the way, called the characteristic equation, or that left-hand side is called the characteristic polynomial of the linear constant coefficient equation. Okay, why is this fact true? Why, if lambda solves this, will e to the lambda t solve the differential equation? Well, just notice that if you take e to the lambda t, you take a derivative of that, that's like a lambda e to the lambda t. You take another derivative to compute what e to the lambda t double prime is, that's lambda squared e to the lambda t. And so if you plug in e to the lambda t in for y into this equation, you'll simply get well, let me not write it up there. You'll simply get the characteristic polynomial times e to the lambda t. And e to the lambda t factors out of everything. And so, this is a positive function, so you might as well divide by it. And notice that you got a solution to the differential equation exactly when this algebraic quantity vanishes. Okay, very nice. So that gives you a very simple description of when that exponential function will solve the differential equation. We just need that lambda to solve this algebraic equation. And this is all the, this isn't just a guess. All solutions will take this form. And by the way, there's a better reason for why we guessed this, which maybe I'll talk about in class, but it's just a guess for now. Okay, so we're going to be trying to produce solutions by solving this. We want to find solutions. They're going to look like e to the lambda t, where lambda solves that equation. Well, notice that this is a quadratic equation, and quadratic equations have solutions. So just recall basic, the real basic thing is the quadratic formula, minus p plus or minus square root of p squared minus 4 q over 2. Yeah, I didn't mess that up. Yeah, okay, you get the quadratic formula. And a number of different things can happen. First of all, you could get two distinct answers out of this. Two real numbers that are distinct, and those will give you two different exponential functions that solve your equation, and they'll be linearly independent. You'll be in business. A bad thing can happen where you just have a single root, where when you have a single solution to the equation, that's what happens when underneath the radical vanishes, and so you don't get any plus or minus. You just get only one solution to the characteristic equation. So that can happen. Either two real distinct ones, a single repeated one. And then, by the way, your solutions might be real numbers or complex numbers. They'll be complex if what's under the radical is negative, and it'll be square root of some negative things. So that's, that'll involve the, square root minus 1. So it might be complex numbers there. But in any case, you'll always have solutions to this equation. And so the real question is, okay, if you have two distinct solutions, whether they're real or complex doesn't really matter. When you have two distinct solutions to this characteristic equation, then that will give you two different exponential functions that will be linearly independent, and you can write down the general solution by just taking combinations of them. What is concerning is what happens when you have a repeated root. So what if you have just a single solution to the characteristic equation? What do you do? Because you need, remember, two linearly independent solutions to write down the general solution. So this fact will only give you one solution. What do you do? Where's this other mysterious solution? Well, it turns out that when you multiply e to lambda t by t, that will also be a solution in this situation. So when lambda is a repeated root, when you only have one solution to characteristic polynomial, or one root of characteristic polynomial, then your two solutions will be e to the lambda t and t e to lambda t. I can explain why that is in the class. Okay, so let's run that game plan here. So here's the constant coefficient second order equation. Let's write down the characteristic. So we're going to follow our strategy. We're going to look for exponential solutions. So look for solutions taking the form e to lambda t. So that leads us to the characteristic equation. In this case, it'll be lambda squared minus 2 lambda plus 1 is equal to 0. So the minus 2 came from that minus 2, and the 1 came from the coefficient of x, which is just 1. Right, okay, so we want to find the solutions. Well, notice that this thing factors. It's lambda minus 1 squared. So we only get one solution to this equation. So lambda equals 1, and this is a repeated root. It has multiplicity too. So the solutions that we get from this method are, first of all, we immediately get, I shouldn't call it y, I should probably call it x, e to the lambda t, so that's just e to the t. That solves this equation. And then from what we just learned, t, e to the t will also solve this equation. It's not hard to check that these two functions are not multiples of one another, so these are linearly independent, and so these are linearly independent. So the general solution is should be x is equal to c1 e to the t plus c2 t e to the minus, or sorry, e to the t for any c1, c2. Okay, that's the general solution. This is just an example where you have a repeated root. You can imagine there's a, you'll do a couple of problems like this, and it boils down to finding the roots, writing down the solutions. If there's a repeated root, then you know what to do. You get this other secret solution by multiplying that one solution by t. And that's kind of the rough outline of how to solve constant coefficient, second order homogeneous equations. So you kind of already see the landscape here. Let's approach the situation where you get complex roots. So, well, I'll explain here. Let's take a look at this equation. So another way of writing this would be like that. We already saw this equation. It's like x double prime is equal to minus x. That equation for undamped oscillating motion, where you have no gravity, and you got this oscillating behavior forever. So we had sine and cosine solutions to this equation. Okay. On the other hand, let's apply what we just learned. That was just from a mechanical intuition. The sine and cosine would solve this, and you can check it. Take two derivatives, you get minus sine. But we just learned how to solve. This is a constant coefficient equation. We know how to solve that. We seek a solution of the form e to lambda t, and then we want to solve the characteristic equation, which in this case would be just lambda squared plus, well, there's no lambda term because there's no x prime term, and then plus 1 for the coefficient next to x. Okay, and whoopsie, this leads you to lambda squared equals minus 1, or lambda itself is equal to square root plus or minus square root of minus 1. And I'm assuming many of you have seen complex numbers before in some format. You abbreviate the square root of minus 1. You treat it as kind of a formal object, even though it's just what it is. You give it the name I. So plus or minus I, where I is just a stand-in for square root of minus 1. I for imaginary, even though it's very much real. Like a real concept. Anyway, so we get, there's some funny business going on here, because we got sine and cosine solutions on one hand, but on the other hand, we're supposed to get exponential solutions. So what's going on with that? So, this gives us solutions e to the lambda t, and e to the, oh sorry, lambda is I, e to the it and e to the minus it. So we got sines and cosines solving this, and we also have complex functions solving this. Now let's make an interesting observation. Because e to the it solves this equation, there must be numbers. So, sine and cosine, they're linearly independent. They form a complete set of solutions to the equation. Any solution can be written as multiples of those two functions. So as a consequence of that, e to the it, it must be able to be written as multiples of sines and cosines. So c1 cosine of t plus c2 sine of t. There must exist c1 and c2 that make this happen. Very strange. I mean, maybe some of you know is not the biggest surprise to many of you, but we can see that such an algebraic relationship must exist from that, fact that I said before about second order equations. That they're, if you have a linearly independent set of them, then the general solution can be written as a linear combination of them. Well, I got another solution. So I know sine and cosine are good solutions. I got another solution here, e to the it. Well, that fact must imply that there's a way of writing e to the it as a linear combination of cosine and sine. Which is, if you didn't know that already, is not intuitive. So that leads us to, this is the actual relationship. There's an algebraic relationship between complex exponential and sines and cosines, and it's this one, Euler's formula. So if you encounter something that looks like e to the I lambda t, you can write it in terms of sines and cosines. This can be written as the complex number, because it's got an I in its formula, it must. Cosine of lambda t plus I sine lambda t. Okay, so this is a fact that will be quite useful. So the subtext here is that you can always find real value solutions to second order differential equations. So even if your exponential functions that you get from that method that we, our general game plan, that can give you complex valued functions, e to the it, but it is a fact that you will always be able to write solutions to such equations in a real form. The complex numbers are not necessary to write down a solution. Solutions can always be written in a real form with no complex numbers whatsoever. And you can achieve this. So suppose you you look at this equation, you get those complex solutions, e to the it and e to the minus it, and then you're like, oh man, that's a bummer. I was hoping to get a real function out of this, real valued function. Well, the good news is, and the procedure that we'll have to do sometimes, is this formula can be leveraged to always write down certain combinations of e to the it and e to the minus it, or whatever complex exponential functions you run into in terms of cosines and sines with no i's, just only sines and cosines. So, there's a process of going from these complex exponentials to detecting the trig functions that are can be written as appropriate multiples of the exponentials. And this is special due to the fact that complex solutions to these things, they come in pairs. From the quadratic formula, there's like a plus minus and then the square root, so that the imaginary part of a root always comes in pairs. Like it's either a plus or a minus. So they come in this one, a plus or minus ib. And the fact that they come in those pairs like that, conjugate pairs, when you reverse the sign on the imaginary part of a complex number, it's called conjugation. Anyway, so roots appear in conjugate pairs, and that allows you to do this maneuver I'm talking about, but have not shown you yet. Okay, so let's do that. Let me show you this trick. So we're going to encounter some complex functions, but I'm asking for the real value general solution. Okay, so let's take a look. So this is linear, second order, homogeneous. I should be going right to the characteristic equation. So characteristic equation here, let's see, it'll be lambda squared plus 2 lambda plus 3 equals 0. Let's see what the roots are. So lambda will be equal to -2 plus or minus square root of 4 minus 12 over 2. And so I got -1 plus or minus the square root of -8. And so I'll get -1 plus or minus I times square root of 8. So there we go, we get 2 complex roots, distinct complex roots. So we get solutions e to the lambda t, so -1 plus I root 8 t, and e to the -1 minus I root 8 t. So let me write those in, slightly, let me rearrange it a little bit. So it'll look like e to the minus t times e to the I root 8t, and e to the minus t, e to the minus I root 8t. Okay, we got complex solutions. So I can write down the general real solution, or sorry, the general solution will be just multiples of these two functions, sums of multiples of these two functions. But we wanted to not just get some answer, we wanted to get real value answer, sines and cosines. So let's do that step that I mentioned in the last slide, but did not tell you how to do. Okay, so note, okay, let's call this x1 and this other function x2. Okay, so using Euler's formula, x1 is equal to e to the minus t. And now let's take this exponential thing and use Euler's formula on it. So here, yeah, well, this is just cosine of root 8t, and then plus I sine root 8t. Okay, that's that. It's a complex, we still got i's. We haven't done anything yet. We just use Euler's formula. And let's do the same thing for x2. I get e to the minus t. Yeah, that's why I took it out. It's not going to get involved in the formula. That's just the e to the minus t is going to hang out. And then what do we got over here? Well, we got a cosine of minus root 8t, and then plus I sine of minus root 8t, because the x2 has a minus sign in the exponent. But let's take a look. So, looks like we can't necessarily compare these functions, but remember, cosine is an even function. You plug in a negative number, like a cosine of 5 is the same as cosine of minus 5, the even function. So cosine of minus root 8t, that's the same as cosine of root 8t. Sine has kind of the opposite property. It's an odd function. Whenever you plug in a number, that's sine is equal to negative sine of negative its input. Or in other words, sine of 5 is minus sine of minus 5. So this here is minus I sine of root 8t. So let's take a look. So for instance, I could form the following linear combination. I could take x1 and add it to x2. That's going to be another solution, right? Linear combination of solutions, so it's a solution. But look at what happens when we add these two formulas. The I signs will cancel out if we add these two things together. They cancel out. So what we'll get here is just two copies of e to the minus t cosine root 8t. Oh, bingo, that's good news. That's a completely real solution. No complex numbers whatsoever. That's our first real solution that we got. Now, likewise, we can do the following. You could take the difference of these two functions, x1 minus x2. Well, what's going to happen there? Then the cosines will cancel, and we'll get 2i e to the minus t sine root 8t. Now, so that's not a real function because there's an I in there, but that's just a constant. So we could multiply that function by any constant and still get a solution. So we could divide that solution, that 2i e to the minus t sine of root 8t, we could divide that by 2i, because 2i is a constant, and dividing won't change whether it's a solution or not. So in fact, just e to the minus t sine root 8t will also be a solution, and it's real value. Okay, great. So we found two real valued solutions just by taking linear combinations of our complex ones and using Euler's formula. That's the trick I was briefly describing above. This will always work. You get your two solutions with maybe complex exponents, use Euler's formula, and then add and subtract the resulting expressions to get real solutions to the equation. Anyway, so the general solution. So the general solution takes the form any number C1 times e to the minus t. Well, actually, let's factor things out a little bit, make it look a little bit nicer. Oh, whoops, in general. It'll look like e to the minus t times C1 cosine root 8t plus C2 sine root 8t. That is the general solution for any C1 and C2. C1, C2. So very nice. By the way, notice that I'll just graph it in red here. This function will have the following kind of rough behavior. It looks like e to the minus t times the trig function. So that'll look like it's oscillating, but then the oscillation gets dampened by the e to the minus t, because e to the minus t goes to 0 as t goes to infinity. So this will have the behavior, or have the look of a trig function that gets dampened. They'll be trapped in between these e to the minus t and minus e to the minus t curves. So it'll be oscillating in between those two curves. That's just the behavior that we're observing for solutions to this equation. Okay. Good. Oh, and one more comment. This trick working heavily relied on the fact that the complex roots came in conjugate pairs, that they had this plus minus structure to the complex roots. That was essential in order to MacGyver our real solutions from the complex ones. If they did not appear like that, then we'd be in trouble. This trick would not work in general. You could imagine, what if the you'd be looking at cosine functions with different periods, and you wouldn't know how to combine them right after that. Okay. Very good. So now we have, at this point, we have a robust understanding of how to solve constant coefficient, linear, second order, homogeneous equations. A lot of qualifiers, but we know how to solve them. You look at the characteristic polynomial. If they're real and distinct, then you get exponential solutions. If they're repeated, then you got that, you know, one exponential solution and then another one that looks like t, e to the lambda t. If they're complex, you got this trick that I just showed you for getting the sine and cosine type answers. And if you get repeated complex, is very similar procedure. No, sorry, you never get repeated complex. What am I talking about? Ignore that last statement. We know how to do these entirely. So let's go to an application. Section 4.4, harmonic motion. So in this section, we'll try to completely understand the following setting: unforced spring mass movement. So, you know, again, the typical thing to think about is a spring with a mass attached to it, sliding back and forth on a greased up table. Yeah. That's really what I'm talking about. Okay. Let's write it in the following form. So this is the equation that, you know, we predicted that we would get something like this. So where this comes from some damping force. Say you could imagine one side of the spring is attached to one side of the weight is attached to the spring. You could consider the other side attached to what are these things called? Dashpot. The dashpot is some like a physical mechanism that, like, you know, suppose you're designing a door, but you don't want the door to like slam. So it cushions the motion if the velocity is very high. So it's something that does that. So that'll have a damping effect. And if you wanted to imagine this differential equation as modeling a specific situation, you could imagine this one, where on one hand, you have a spring that's forcing your motion. And then on the other hand, you have this dashpot, which says that, oh, if you go too fast, I'm going to dampen your motion in a way that's like this, 2c x prime. Okay, so you got that, and you got this one from the spring. So basically, you only have two forces acting on you: one from the spring, one from some damping thing like a dashpot or air resistance. You could think of that. Anyway, so you got these two constants that completely describe the motion. They have to do with the mass, the spring, and the damping. We'll see in an example how these numbers come about. Okay, so, but I just want to write the equation in the following form, you know, in that form where you got a 2 next to the c and the constant next to the x is a square. It's just that, you know, it just, in a given situation, to figure out what the c and the omega naught are might just require some work. But let me just write the equation in this form. We know that it will take something like this form, but it might take some consideration to figure out how c and omega depend on the mass, the spring, and the damping. You have to work that in a given situation. But anyway, so you get an equation like this. Let's write it in this form, and let's go from there. Okay, so first let's consider the undamped situation where there's no dashpot, say you just have that harmonic motion. So in this case, we'll have, if you look at this equation for this motion, just the spring and the mass, you'll get a characteristic equation with two complex roots. And if you do the work that we did in the last example, you'll find that the general solution looks like this. Just the sum of sines and a sum of a sine and cosine. Where the omega naught is going to be the, affecting the frequency of the trig functions. Okay. Okay, in this setting, basically the whole motion is described by this one number omega naught, and that has a special name. It's called the natural frequency of the system. So that's the story with undamped motion. The solutions will just be sines and cosines. Now, you might remember, or you might know that if you have the sum of a sine and cosine function with the same period, then you can actually write that as a single trig function. For instance, a cosine function. So that's what I'm saying here. So you can actually write that solution down as a single trig function, which is obviously something you would want to do because, well, let me not say obviously, but it's something that you would like to do because that's a more simple description of the motion. Okay, so recall this, trig fact. If you have a sine cosine, if you have a sine function and a cosine function with the same period, then you can always do this trick. You can write that as a single cosine function where its amplitude is related to the amplitudes of the other ones by the following equation. A squared is little a squared plus little b squared. And then you might have to shift that cosine function to the left or to the right. And that is according to whatever tangent to a over b. Tangent of that little shift will be equal to a over b. So yeah, this will be advantageous to do because then you could describe the, it's not obvious how, what the maximum value of a solution would be if you write it as the sum of two trig functions, but it is obvious if you write it as a single trig function. And it's obvious what the maximum and minimum values will be. It'll be a. Okay, so let's wrap up with, let's summarize that idea, or expand on that idea by taking a look at this example. So let's look at the situation where there's no damping. So just a spring on a 3-step table, oscillating back and forth from its equilibrium. And so what do we need to do? Well, we need to, in order to describe the system, we need to know, okay, what the mass is. So the mass is 2 kilograms. And the spring, we need to know something about that. That is described in the following way. So if you act on it with 5 newtons, that will stretch the spring 1 meter. Okay, so recall, so in order to figure out what that means for the motion, so the force from the spring, that equals minus some constant times the position away from equilibrium, the masses. Okay, so what did we just find out? If I stretch the spring a meter, so that's like x is 1, so I move it back a meter, then the force that the spring is, it requires 5 newtons to stretch it that way, so that means the spring is acting in the opposite direction with 5 newtons, so you have 5 there. So K will be minus 5. Or, probably, let's keep it positive. So it'll be, the spring will be acting in the opposite direction, so K will be positive 5. Okay, so force is equal to mass times acceleration. So what does that mean? X double prime times m is force, which there's only one force at play here. It's from the spring, and that is just like acting like K times x. with a minus sign. Okay, or in other words, x double prime, plus k over m, x is 0. So that's the differential equation that describes this motion. So let's solve it, and let's see, what do we want to answer? I didn't even read the whole problem. We wanted to pull the weight a half a meter, let go, and watch it oscillate, and see what happens. What's the amplitude of that motion? Okay, so let's solve the equation first. So the characteristic polynomial will be lambda squared plus k over m is 0. Or in other words, lambda will be plus or minus square root k over, oh, sorry. I know what k and m are. Why did I do that? Let's put those in right here. So k is 5 and m is 1. So the square root of 5. Plus or minus I times square root of 5. So that gives complex solutions e to the, I5, well, let me just write it out. That gives solutions e to the I root 5t and e to the minus I root 5t. Applying the procedure that we learned about recently, that will give real solutions. X1 is equal to cosine root 5t, and x2 is sine root 5t. And so the general solution will be, C1 cosine root 5t plus C2 sine root 5t. Okay, so that's the general real form solution. Let's figure out what the constants are, because it's a real physical system. We should be able to figure out what the exact formula is. Okay, so what are the initial conditions? So we pull the weight back and then let it go. So the initial condition, x at times 0 is equal to half. And then I just let it go. So that's the same thing as saying that the derivative, well, it's not the same thing, but I'm not pushing it or anything like that. I'm just letting it go. So its initial velocity is 0. Okay, so x at 0, well, let's plug in 0 in for t. What do we get? Plugging in 0 in for t, well, cosine of 0 is 1, so we get C1. And then sine at 0 is 0, so you get nothing there. So right off the bat, that tells me that C1 is a half. Very nice. Okay, let's take a derivative of this function and plug in 0. That will, the derivative of cosine is going to be a minus sign. When I plug in 0 into that, I'll get 0. And then over here, I'll get the root 5 C2, times cosine of 0, but that's going to be 1. That whole thing should be 0. That means that C2 is 0. Okay, so we just figured out the whole motion. So x of t, the solution, will just be 1/2 cosine root 5t. And the amplitude, of course, the amplitude is a half. It so happened that I did not need to use that remark that I just explained in the previous slide here. But if the initial conditions were so that you had both a non-trivial sine and cosine, then to figure out the amplitude, you would need to use this equation. Oh, give myself more space. Okay, so let me just touch on this and we've already gone for quite some time here. I'll finish up the more in-depth discussion on this in class, either on well, probably on Friday. I might have a short remark, maybe share a video on this to describe it in more depth. But let me just say, if you are interested in the, well, let me just say the next thing to study is what happens when damping is involved. Say that dash pot situation I said earlier, where you have that mechanism which dampens your motion if you go fast. It'll dampen you and it'll act on the whatever opposite direction that you're going. Okay, so and again, that is described by a force taking the form of just a number times x prime. That's how it acts. Just it's proportional to how fast you're going. So you get this extra term that looks like a number times x prime. But let me write that number as 2c, where c is some number. Okay, why did I do that? Why did I want to write it as 2c, and why did I want to write the constant next to x as something squared? Well, then the quadratic formula has a really nice form. So that's the only reason I do that. By the way, remember c and omega, they're non-negative numbers. Okay, so you look at the characteristic polynomial and find the roots, you'll get this business. You'll get, this formula. Okay, and then, from what we know in the previous section, we know how to write down the solutions. They might be exponential solutions, they might be complex, and then you got to figure out what the sines and cosines are. But we know how to write down solutions, real valued solutions to the equation in this setting. But we want to interpret what is going on in terms of the physical situation. So we know what the formulas are, but we want to interpret that in terms of the situation. Well, there's 3 different situations. Or, depending on what the mass is, how the dash pot, how the dampening is working, and how the strong the spring is, there'll be 3 different situations. Either what's under the radical is negative, or it's positive, or if it's 0. Okay, if what's under the radical is positive, right? If what's under the radical is positive, then you'll get solutions that'll just get, so you get exponential solutions. E to the minus, I don't know, I'll just call it like, b times t, where b is a positive number. I mean, you can see that it will have to be positive. Is that right? Oh, yeah. The exponent will be negative, b will be positive. Okay, so if c is bigger than omega naught, then you just get exponential decay from your solutions. If you follow through the procedure of the last section, you'll get solutions that look like e to the minus positive number times t. That's just exponential decay. So that's like you pull the spring back, you let go, and the damping is so strong that there's no oscillation whatsoever. You just slowly go back to equilibrium. And so it makes sense to call this an over-damped system. The damping is so strong, you don't get any oscillation whatsoever. You just get, ooh, Okay. If what's underneath the radical is 0, then you get solutions of the form, so get solutions. Then you have a repeated root situation, then you get solutions that look like e to the minus bt, or t e to the minus bt. Okay, which is a similar kind of behavior. No sines and cosine, no oscillating. You'll just slowly go to equilibrium. But it's kind of like, it's slightly different motion, so it has a slightly different name. It's called critically damped. That's like, it's a cutoff point between 2 different behaviors. So over damped behavior, that's like so damped that you don't get any oscillation from the spring. The dampening is so much stronger than the spring that happens. And then the third possibility is what's under the radical is negative. You get complex roots. That gives you sines and cosines after using Euler's formula. So you get things that look like e to the minus bt. You get solutions of the form e to the minus bt times something that's like omega t, something like that. Exponential function times a trig function. And so that gives you that nice oscillating, that damped oscillating behavior, where yeah, you're being damped, but you get the spring still lets you do the wiggling, the oscillating a little bit. Okay, and that situation makes sense to call it underdamped. So you have the cutoff is when the system is critically damped, and if the spring is stronger, then you're in the underdamped setting. You have a little bit of oscillation before as time goes on, you'll converge to equilibrium point. Your mass will eventually settle down. And if the spring is weaker than the damping force, then that's overdamped, and you get this behavior. You just get exponential decay to the equilibrium position. Okay, so maybe we'll do an example like that in class on Friday or in the lecture over the weekend, depending on how much time we have, how many questions there are in the Friday lecture. But let me stop there. So we covered a lot, figured out how to solve constant coefficient linear homogeneous equations. I think I said all the right words. So that's the main new tool, technical tool we learned. The fundamental physical application example is this spring motion. And we just rounded out the lecture talking about that. Okay, so let's end there, and we're about at 2 hours. We'll end there and pick up again next week. All right, thanks for your attention. I'll see you in class.